Greetings. It's Professor Jamison-Hooks here again. And today we're going to go high above the earth to the cirrus clouds that drift at 12 kilometers. And they're filled with tiny droplets, ice crystals, and traces of oxygen that control how sunlight and heat move through our atmosphere. To study them, we send out a radar chirp, a signal that sweeps smoothly across frequency like a rising note. As it travels through the cloud, each droplet and molecule reflects a slightly different frequency, revealing its size, motion, and composition. In this airborne radar diagram, the aircraft transmits chirps downward and receives echoes that pass through oxygen and water vapor absorption lines. The peaks at 65 gigahertz and 69 gigahertz mark oxygen, while those near 167 gigahertz and 174 gigahertz trace H2O. Measuring reflected power at those frequencies let us estimate pressure, P, humidity, Q, and temperature, T, through the cloud column. Inside the receiver, a digital down converter mixes the wideband chirp to baseband, low-pass filters, and down samples, all on an FPGA. Every such design begins with the frequency plan in MATLAB, the blueprint that defines where signals live in spectrum and how we'll move them through digital hardware before writing any HDL, hardware description language. From there, scientists reconstruct the fine spectral fingerprints of water and oxygen, the foundations of weather, climate, and life itself. And in a future video, we'll explore the next step, applying a matched filter to measure the precise delay of each echo, revealing how far every droplet and ice crystal lies within the cloud. Subscribe and follow along as we take this signal from the sky to the screen, turning radar echoes into real scientific insight, one FPGA design at a time. So here we're going to walk you through how a chirp signal is digitally down converted, the same kind of signal chain used in radar communications and even astrophysics instrumentation. We'll start with a 10 to 20 megahertz chirp, mix it down, low pass filter it, and finally downsample by 2, showing exactly what happens in both frequency and amplitude. We begin by setting our sample rate to 60 megahertz. That means our Nyquist frequency is 30 megahertz. Anything above that will fold back in. The chirp sweeps from 10 to 20 megahertz, and we'll mix it with a 15 megahertz local oscillator. Finally, we'll decimate by 2 to get a new sampling rate of 30 megahertz. Here, we generate the chirp and multiply it by a real cosine at 15 megahertz. That produces two components: the difference band from -5 to +5 megahertz, and the sum band from 25 to 35 megahertz. Before we throw away any samples, we must make sure we don't alias. A simple FIR low-pass filter keeps only the -5 to 5 megahertz baseband and rejects the higher frequency sum components. Now we downsample by 2, keeping every other sample. Our sample rate drops from 60 to 30 megahertz, which also halves our Nyquist to 15 megahertz. Because we filtered first, no aliasing or folding occurs. On this separate plot, the blue trace shows the filtered signal before decimation, and the orange dash trace shows the decimated spectrum re-expressed on the original 60 megahertz frequency axis. Notice how the dash spectrum spreads from -10 to 10 megahertz, twice as wide, and its amplitude is about 6 dB lower. So I hope you've enjoyed this presentation. I look forward to seeing you next time as we continue our path from here, the digital down converter, to the FPGA, from the clouds to the hardware. Have a great day.